Hello. In our last video, we introduced the concept that sometimes the derivative is not defined at a given point, even though the original function is. And I'll show you a little bit of some of the observations that you can make on the graph of a function to see if its derivative will be defined at a given point or not. So let's say that you had your coordinate system like this, and your function looked like this. So here, our derivative right here is just a vertical line. And so by the way, this is actually the function of f of x is equal to x cubed plus c, just because I moved it on the x. Oh no, I'm sorry, so that's not f of x. Sorry. So f of x plus c, and cube root of that. So the c is just, you can just ignore it. It's because I didn't want to do it exactly here at 0, 0, because then some people just think that that only happens if it's in the y-axis. I know it's just that it's a vertical line regardless of where it's found. You see a vertical line as the tangent line. So that's our tangent line. And when you see this happen, the derivative is undefined. Why, you may ask? Well, so remember that the derivative is the slope of a tangent line, and the slope of a vertical line is infinity, which is basically undefined for that specific tangent line. So next, if this is your x and y coordinates, and your graph looked maybe something like this. So having a sharp point, here we see a very sharp point that if you were to look at your tangent line, first it would be something like that. Then, let's change color. Then something like that. Imagine that it's touching it. My drawings are awful, but imagine something like that, and it just seems to converge to this line right here, right? But all of the sudden, if you were to look at the right, it's not like that. So this is our first tangent line. This is our second, maybe like so. Our third. And by the end, our tangent line is like that. So we see that the slope of our tangent lines coming from the left and coming from the right are extremely different. It doesn't converge. So, for example, if you were to look at this point right here, well, this tangent line is going like this, then it's going like that, and it's converging to this line right here. If you were to look at how it approaches from the right, well, from the right it's like a little bit like that, then like that, then like that, and it eventually approaches what we had before, this line right here. So we see that the tangent line, if you approach from the left or from the right, you get the same slope. However, we see that in this sharp point that we had right here, if you approach it from the right, you get a very different tangent line than if you approach it from the left. That means that the slope there is undefined. And so that is also just by observation, a very easy way to tell if the slope there is undefined or not. to see if there is a sharp point, that if you were to draw tangent lines going from left to right and approaching that point, and tangent lines from right to left and approaching that point, that you get very different lines. And so just if you want to graph it or try to find the derivative of this graph manually with the definition I have given you throughout the previous videos, and you try to find the definition, the derivative of this function right there, you will see that the derivative is undefined at 0, 0. Same thing with this one. You can just use the square root of x, like so, and you will see that at 0, 0, the derivative is also undefined. Another way, another graph that you can also see that the derivative will not be defined at a given point is just if f of x is the absolute value of x. So as you might recall, this is the graph of the absolute value of x. And this is exactly what I said before in this case, but in a very simple manner. So here, as you might recall, like I said before, the slope of a linear line, of a line is just, the derivative is just the slope. So see, here we have a positive slope, and on the left, we see a negative slope. I mean, you could change slopes. So, for example, if you were to have a parabola like this, here you have positive slopes. Negative slopes. Yeah, my bad. Negative. And here you have positive slopes. But as you move closer and closer and closer, you see that they actually very nicely approach the same value. It's not like one of them wants to stay positive and the other one wants to stay negative. They approach 0 and then move to the negative side or move to the positive side, depending on what direction they are going. So here, actually, our derivative is well defined everywhere. However, here, none of them are approaching 0 or approaching the other values. They are going from a very positive value to a negative value completely. So here, the slope is undefined, and it would be a little bit harder to use the definition of a derivative, but you could try and see what happens. And last, another way is when you have a piecewise function. So, for example, let's say that you combine two graphs like this. And so let's say that here before the y-axis, we have f of x is equal to 1 minus x squared. And to the right of the y-axis, we have y is equal to 1 over x plus 1. So the same thing I said before, here you have this tangent line right like that. Approaching from the left, you have a completely different tangent line. So here they do not agree and the slope is undefined. Something to keep in mind is that this is a function. So this piecewise collection of these two f of x are turn out to be a function because the function is defined everywhere, the x do not repeat, and all of that good stuff. However, and if you were to plug in 0 in both, you see that in both cases f of 0 is 1, so it's continuous. There are no holes, no jumps. But still, the derivative is not defined at their union because the slopes are not equal at their when you transition from one function to the other.